Excuse me. So if you do all that for the nearest neighbor, what you end up is this shaded area. You see, so this is half of this. This from here is half of this, and this from here is half of this. You carve out a little point in here. And this is just done in 2 dimensions. You can imagine that you have another dimension in 3 dimensions. You can create a volume like this. Here I create an area because I have 2 dimensions. So this volume or area is what I call a Brillouin zone, the first Brillouin zone. Okay, so just go to your nearest neighbor in residual space, take the bisector and create a zone. And something very interesting happened. If you look at this Brillouin zone, so here I have a residual space lattice, many different points that I got. Right, this is my origin, and I create the first Brillouin zone. So from this point I draw all my nearest neighbor, and I find the smallest volume. And this is my smallest volume. This is my first so-called first Brillouin zone. Then I go further. I go from here to here and take the bisector. From here to here, take the bisector, and so forth. And then what I got is that I got this bigger square that I have, right? And this bigger square contains the first Brillouin zone. Okay. So what I have just created, is the so-called second Brillouin zone, which is highlighted by this red triangle, the 4 red triangles. What you can see is that if I fold the red triangle back into the center square, the area is exactly the same. Okay, so one interesting point is that the Brillouin zone, the first Brillouin zone had exactly the same volume as the second or third or fourth and so forth Brillouin zone. So all the Brillouin zone is identical in size. Okay, and why is that? And that corresponds to the fact that you have periodicity of the unit cell, and that created this so-called Brillouin zone. And they are very powerful when we're talking about the electronic structure, as we'll see later when we're talking about the electronic structure of the solid. Okay, so you can keep going. So here I may have a better way to show you this. So here I have first Brillouin zone in here, right? And then I created my second Brillouin zone like this, and do exactly the same way. I keep expanding my bisector to more and more points outside, right? And so, for example, the first Brillouin zone, I create the bisector here. Okay, so this will be my bisector here. And I have this point, this point, this point, this point, and this point. This 4 point, I create the first Brillouin zone. To create a second Brillouin zone, I go to this point, the bisector, right, and this point, and this point. You see? So I got this bisector. So I got this diamond structure. And if you exclude the first Brillouin zone, you got hatchet area labeled 2. And you fold it back in. The area 2 is equal to exactly the open area, like this, the first Brillouin zone. And then you can do the same with the third one. The third one will be going from, let's see, the third one will be this bisector in here. So it will be from this point to this point. And I draw a line from this point to this point. And you create this red highlighted zone, and this is my third Brillouin zone. And the fourth Brillouin zone will be these little hatches like this. So as you go further and further out, the zone is chopped up, but the size of your zone is always the same between the first, second, and third. And that is important because this is kind of periodicity, introduce the idea of periodicity into crystal, but in residual space in terms of Brillouins. So here, for example, is an example of the fourth Brillouin zone. The hatchet area, right? This hatchet area that highlighted in hatches in some shaded area is the fourth Brillouin zone of this residual space that And the reason why is useful, I just briefly introduce this, and I come back to this when we talk about electronic structure, is that you can consider the energy level diagram. You know, you think of it as MO diagram. You can extend it, draw it in residual space. And if you draw the sort of think of it as electron density curve in residual space, it will look like this in Brillouin zone. And you'll be able to fold them instead of drawing it to infinitum. You can fold your Brillouin zone, and then you can, because of periodicity, you can study just one zone instead of studying the whole big area. This all sounds very abstract, but I want to just mention this, but I will come back when we explain this diagram a little bit more. Okay? So here I just say, for now, I just say the Brillouin zone give a convenient geometric interpretation of these diffraction phenomena. So we have, from before, we have k 1/2 g equal 1/2 g squared. And so Brillouin zone is, so any vector from the origin, this is my origin, to the zone boundary, right? So you can think of this, my Brillouin zone, right? This is my residual vector. So my vertical plane here is my zone boundary, right? So any vector that hit the zone boundary will satisfy the diffraction phenomena because the bisector will give you 1/2 this. So any of this will give you diffraction phenomena, and it will satisfy the Ewald construction. So so I like to just introduce Brillouin zone and perhaps confuse you a little bit, but then next time when you see this, you will understand what Brillouin zone is all about. Okay. All right. So so now I want to switch gear a little bit. So we talk about diffraction from the solid, from looking about point of view, and we want to describe perhaps a little bit more in greater detail about the structure of the surface itself. And I want to go from very simple